Good, you can go and start. I'll fix this.
Afternoon. Yeah, so hi, I'm Tom. I'm the lead developer on Talks. So Talks is a joint venture between Cresset and Elixir, and it's a so yeah, it's the DMTA platform, just for your small molecule drug discovery. So as a web platform, we deploy in the cloud on AWS, and we also use RDKit in quite a lot of places. Core in the application itself, but you'll see the little green numbers are molecular properties that we're calculating with RDKit. So a challenge that we're dealing with at the moment is kind of scaling up to deal with a lot more molecules and deal with kind of asynchronously calculated properties. So we're building a service to do that, and part of that is migrating our RDKit properties to that service. So what is a Lambda? A Lambda is serverless computing. So it's not serverless, it's AWS gives you a server and then it runs functions on it, but you don't have to worry about that server itself. And as we've seen this morning, our RDKit property calculations, which were loops of underscores and stuff, and now is just a single function call, translates really well to a Lambda function. You can just stick here on this function and get you my results. So we started to figure out how we could migrate that to a Lambda. Code Lambda is one of the options, which just takes a blob of up to 50 megabytes of code and any dependencies. So the code itself is now just going to be one line probably, but you also have to include RDKit in your bundle. So actually when you include RDKit in your blob, it kind of goes above 50 megabytes. So we face a bit of a challenge there, but we got around it in kind of a hacky way. So you'll see our script here, which is systematically deleting parts of RDKit while running the function so that it still works. And actually we managed to get through quite a lot of bigger blobs and getting rid of pillow and stuff. And we got it down to about 46 megabytes and it still runs. That's not really a great solution. So the other option you can use on AWS is Container Lambda. So what this is just a Docker image, which includes your whole runtime environment and your code, and it just spins that up and runs it instead. So that allows us to include the entirety of our RDKit. So in this case, we were doing panes flagging. So the thing that we couldn't do once we deleted pillow and half of our RDKit was draw anything. So instead, you just build a Docker image. You can also include stuff like libx render, which is necessary for doing all of this drawing. Build your Docker image, deploy that. And there's an example of using Boto3, which is the AWS library, to call that and get back a panes annotated structure. The containers, while they allow you to include more code, they do have a few disadvantages in that your cold start is going to be a lot longer, and you have to actually manage and deploy these images yourself rather than just uploading a blob of code. And of course, we always think about security, because then we have to manage what's insecure in our environment rather than let AWS do it. So the other thing is it worth doing it on Lambdas? So looking at the actual time to get your result, it is significantly longer than just kind of running it locally. It's up to 100 milliseconds, probably even more. But what it does offer you is burst scaling. So you can, I think AWS quotes up to 18,000 concurrent immediate tasks per Lambda, and you can probably request more. So scaling your own infrastructure to that comes with challenges, especially scaling it back down to 0. cost-wise, I mean, these are pennies anyway, but it turns out that it's a little bit more expensive, but then you're not paying for it most of the time. And yeah, there's overheads either way. That's it. So thanks to Harry and Amelia who actually did this, and I'm just presenting for them. Thank you.
You should, it won't work until I have your presentation up, but it should work after we do that. You will use that? Yes.
Good afternoon. So I'll give you a little bit of insight on how we treat molecules at Novartis. There's, of course, with a big organization, this is just one way of doing it. So I joined Novartis, and one of the problems I was given is that we had this huge database of millions of compounds, but we wanted to give the chemists a good intuition on how these compounds looks like in the real world. So they're not, of course, flat like a graph. They're like 3D, docking in a solvent, etc. This can be quite a complicated problem to solve, and with that, I had to do a lot of approximations. And following up on yesterday's discussion, one of the problems we had to solve is the tautomization. So the problem is we have a very big database. I need to compute conformers, tautomers, and protomers for all our compounds, and still do it on all the registered compounds that we get every day. And that could be several hundreds, and sometimes to be spike of 1,000 digital compounds. I could just turn this around and it'll be fine, right? Okay, so I don't have enough time to go into the details, but just to note that every single bullet point could have been a talk in the end. But focusing on the graph enumeration from yesterday's talk, there was discussion, how do other people do it? The way we do it, and this pipeline specifically, is that we generate as many Tautomers as possible using commercial softwares. Most reliable, I found that Unicorn is the one that works very well. And then we use quantum chemistry to get the most accurate Tautomers. So we generate a couple of conformers on a Tautomer, and then we calculate the energy in water. We find the lowest Tautomer with a threshold of 7 kcal/mol, and then we include all those Tautomers. And then for all those Tautomers, we generate using internal model all the Protomers. And then for the Tautomer-Protomer enumeration, we then generate a lot of conformers. We are using OpenEye because I did not benchmark the newest RDKit conformer set. And again, what we are doing with all these conformers is that we will filter them. So I do this a little bit different than usually. So usually you would use like an RSD to do the filtering of it. But I didn't want to be biased towards big molecules with small changes. So I look at the very fast surface accessible solvent area and the Geistinger charges to get how is the shape of the molecule and how is the charges distributed. And using that, I'm using clustering techniques to find the most unique conformers in a set of conformers. And then all these conformers, Tautomers, and Protomers, and then put into a database, which then can be accessed by our internal resources to make a molecule wiggle. So I will note that I asked my boss if this is something that people are actually using, and he says he's definitely using it every single day to just give the molecule a little wiggle, and then gives him hopefully a chemical intuition. In the end, the practical is that there's a lot of different external programs that I need to wrap. All of them have their different ways of executing command line, input format, etc. The one thing that brought it all together is that I want to wrap all the functionalities in the RDKit object. So I didn't want to reinvent the wheel and generating a new Python class to contain molecular properties. And so all the different quantum chemistry programs and cheminformatic toolkits, we all wrap that using RDKit. So if you have a null object, you can just call a functionality and then get it out. So that means there's in-house, there's 3 ways of using it. So there's the Python library. People are using it for like machine learning. So if they want to get like really fast descriptors for the compound, they can get that. You have the command line interface for common tasks. And then there's the REST API interface for the database that have been used by our internal tools to fastly get the 3D molecules. Some of it is in-house and internal logic. The open source part is on GitHub already, and I'm hoping to move more and more about internal resources there. And with that, I'll say thank you.
Hello. So I'm Grégori. I also work at Novartis, like Jimmy, actually in the same team. And my talk is about putting RDKit in the hands of the users in a corporate environment. So I'm going to quickly show you how we leverage a software called Datagrok. Paolo yesterday mentioned it shortly. So we developed a fully integrated interface to help lead optimization of small molecules. It's a platform getting data from different sources. So we have, for instance, a virtual compound that you see here at the bottom left. We can query our corporate database to search for a particular project, compound belonging to a particular project, bring in admin data, activity data. It's all connected to the different applications. We also have in silico models, for instance, to predict admin endpoints. And the last bit that I'm not going to talk about is at the bottom right, we have this one pager where you see tons of data for one single compound, including the possibility to wiggle the compound. So this is the front end. As I said, it's based on a commercial application called Datagrok. It's a small company, a startup, basically. I think right now they have 25 employees. And the reason why we went for Datagrok versus, for instance, Spotfire is that they are listening to us. So if we come with requests, they would just implement, or like we work together to get the features implemented. And the nice thing about Datagrok is that it knows chemistry out of the box. So you can load a file with smile strings and the compounds will be rendered. And put all these little boxes everywhere, and this is where we leverage RDKit. There are some parts that are leveraged in the backend. For instance, we do automatic air group decomposition. So for one analysis, the chemist can draw their main scaffolds or their main compounds, or series and scaffolds. And when we load an analysis, we will do automatically air group decomposition to, for instance, allow much molecular series analysis directly in the interface. We also compute fingerprints, again, using RDKit so that we can display a UMAP projection. Just a few examples. And on the front-end side, we can do in the client substructure searches. We can also depict the structure and do highlighting directly on the structure. And we also, this is what Paolo showed yesterday, we have also directly the possibility to export the molecules as PNGs, but also SVGs that you can put it in an email. You can generate a PowerPoint slide that will look exactly the same as this table here. What we are looking into right now, and this is the exciting part actually about this short presentation, that we also want to leverage some more advanced features. The idea is that every expert, for instance, a data scientist or a CAT scientist, could develop small applications or functions that leverage, for instance, RDKit or the RDKit.js. So I put together a small example when the user just selects one compound, like what you can see on the top left. It will execute a script. In this case, it's a JavaScript script. I have it on the next slide. that will perform a lookup against Campbell. So we have an internal instance of Arthur. And what you get back is a subset of Campbell. I think I bring back 20 compounds, and then you can directly render it also in the client. And what you can do as well is to have another type of function. You can add that directly to the main table and then save it, export it, etc. So I think it will be a way for the future. It's something we are still investigating, but I see a huge potential for, again, for instance, cat scientists to have a closer interaction with the chemist, with the scientists working on a project. So this is the script. It's a bit small probably, but I leverage RDKit.js and also do asynchronous call to Arthur. And then eventually what you get at the end is I process the results. There's some HTML going on so that we can do a nice rendering and add that to the table. And that was already my last slide. Many people involved in this big effort, this insurance effort. Some were not there anymore, for instance, Nick. Thanks, Nick. I remove you from the slide, sorry. And thank you for your attention.
And the next speaker should be somewhere towards the front. Okay, good. I didn't see you guys behind me.
Good afternoon, everyone. We are Vinith and I'm Michel, both working at the Czodrowski group, and we developed some tools and applications that make chemists' life more easy. Some of these tools are hosted on our Czodrowski website and are going to be presented in the following lightning talk. With that, I hand it over to Vinith.
So thanks, Michel. And let's start with the PK website. So the PK website is a project which was started by Hadron Rosenboom as a bachelor thesis project and by my supervisor, Marcel Bertelschot, and was further developed by myself in the areas of the backend and front end. And what is the PK website? So the PK website is a browser-based interface which was developed for users to allow to enter a custom assembled database with multiple data sets to search for molecules based on PK values. So if you would like to know more about our used data sets, just go to our GitHub repo, and I also referred the paper to it as well. So let's go watch what's the PK website in detail. So as you can see, this is the UI of the PK website, and we are using the Marvin sketcher to sketch our molecules. And the first feature is a similarity search. So what is a similarity search? With the similarity search, we are calculating the Tanimoto coefficient. We are using the fingerprints of our query molecules and our database molecules. And with this slider, as you can see, we are setting up our lower limit of our similarity. The second feature is the subsector search. So we are drawing our molecule. This is going to be converted into a smarts pattern. Then we are searching for matches in our database. And then we are highlighting our patterns in, I think you can see it in red colors. And the cool gimmick is the caching system. So it's enhancing our time efficiency. So if you are searching for a query molecule, like somebody else, then you will get a definitely quicker response.
The next tool we like to present is an application for the automated analysis of mass spectrometry data, more precisely for the analysis of organic samples or sedimentary samples. And we were approached at the beginning of the year by the analytical chemistry group in our uni. And we were asked if we can help them for their manual analysis of their analysis data because it was prone to errors and also it was really time consuming. So your task with the following questions: how can samples evaluated only by the molecular formula and of course the intensity? And how can ideally a large amount of data be analyzed automatically? This is why we came up with the Van Grevelen tool. And initially, it only had rudimentary features like a drag and drop a function of your data, subset filter of your data, and you can also annotate the strongest signals. But has been then, since then, a lot improved. We have nice front end, as you can see here, but also other functionalities like calculating the carbon oxidant states and also getting the properties. And if you want, you can check out the tool on this QR code. And if you happen to have complex MS data on your phone, you can also analyze your data.
So yeah, let's talk about the game changer project of Professor Czodrowski. So he approached me regarding a problem. So the problem was he's giving the lectures in quantum mechanics and computer science, and he has prepared a lot of Jupyter notebooks, but he forgot to prepare a script for the students. So then he asked me, shall we appoint the students for this work who is going to create a script in a long-term process, or I'm an automation enthusiast, so if I have another solution for this. So I started to search for solutions, and that should be time efficient and should be applicable for all of his future lectures. And it should be easy and user-friendly as well. So then, yeah, the Jupyter book template was created. I will show you later how such a book looks like, but now I would like to tell you more about how you can use it. So first of all, fetch a repository, then create your own Jupyter notebooks inside of this. Then, or you can as well upload your own Jupyter notebooks inside of the repository. Then, yeah, set up these two different YAML data, and that's it. The integrated GitLab CI will automatically deploy a Jupyter book as a GitLab page, and that's it. If you would like to do changes, just do it. So it means commit, push, and that's it. And the GitLab CI will automatically update everything for you. And yeah, that's it, I guess. And here's an example for this. Thanks.
Thank you.
Yep.
You guys were in Google Slides, right? You sent me a PDF.
Okay, I'm Michel, this is Joschka, and we want to tell you about the Kinodata 3D project, which we did together with Verena Wolf and Andrea Volkamer. And in this project, we are interested in finding and analyzing ligands for kinases. And in particular, we want to analyze and find those ligands using three-dimensional structural models, particularly deep learning models. But these deep learning models are pretty complex and require lots of data, which we usually don't have, especially three-dimensional complex data. So we asked ourselves the question whether we could generate more structural three-dimensional data using the available kinase informations and using the knowledge we have on kinases, which is a bit of a good test bed for other more complex proteins we don't understand as well. So in particular, we have activity data, which is far more abundant than the structural data. So we have a couple of 100,000 activities. And we somehow want to combine this with the structural data we have in CLIFs. And the main idea is to use template docking. So recently, as in last weekend, the preprint came out for a redocking study, which indicates that template docking actually works really well for kinases. So we went with this approach, and this works by first searching the PDB using fingerprint similarity for similar ligands for the same target protein, and then fitting the ligand in question to the shape of this reference ligand. And finally, we used the redocking data from the study I just mentioned
to rank our target or rank our final structure's quality. And this we then feed onto the machine learning models. Okay, thank you. So in order to evaluate the utility of this data set for deep learning models or machine learning models, you obviously need some machine learning models. And so this figure isn't really telling you in detail what they're doing. All you need to know is that all of them are basically graph neural networks, but what's more interesting is the input they're receiving. So we basically have 3 baselines, all of which do not use any kind of structural information, in particular, like not the pose of the ligand. So the first one is basically just a ligand-based screening. So it receives the molecular graph of the ligand and puts it into a graph neural network. And the second one extends that approach by basically also including information about the binding site, about the pocket. So you get the residue sequence and put that into a transformer. And these two are then combined for making a prediction. And then the rightmost 2 models are basically very similar. So that's sort of like the best thing you can get in terms of a fair comparison. So the one on the right is basically like the structural model, which basically receives the whole complex, like the ligand and the kinase as a complex. And it constructs a graph based on their relative positions and also takes into account like features like distances in between atoms and so on. And the one on the left is basically an ablation of that model where we remove all of that information again, but the whole like neural network architecture and hyperparameters are basically exactly the same. And for evaluating these models, we just trained them on the data set Michael just mentioned for predicting binding affinities in terms of PIC50 values. And if you do that, the results sort of like look like this, and the figure is a bit broken in the PDF, but I think it's fine. So what this figure is basically showing is the results of training and evaluating the models on a scaffold 5-fold split of our entire data set. And so the blue one is the ligand one, then the drug-target interaction model, and then sort of like these very 2 similar models where the red one is the one that uses the in silico structural information. And what you can observe is that in particular, like if you apply this model and use it on dot complexes where you sort of have an idea that these are of high quality, then it works well. So you get a benefit from considering this structural information. But what I also really like about this figure is that it shows that deep learning isn't like some kind of magic. If you have like docked poses that aren't like accurate at all, then including this information in a machine learning model won't help you. So it's just as good as sort of like the baseline. Okay, so I guess I would like to conclude this talk by thanking especially Professor Andrea Volkamer and the whole Volkamer group, and also all of you for your attention.
Thank you. My name is Esben. We need the slides. Okay. So I'm going to talk a little about some tool we made last year at the hackathon and that have matured. So first we will start. We can go to the next slide. Is it this one? Oops, too long. Yeah, so this is a completely imaginary situation. I hope you can read the chat, but it's me who is chatting with Brad, and he found some file about a Scikit-Learn model that was built a long time ago. And unfortunately, there's not really any information about this Scikit-Learn model, and the postdocs seem to be missing in action in India, and maybe he will come back in some months. So let's see how I fare when I try to investigate this model. So we try to unpickle it, and we get this error. There's something called Scikit-Mol that is missing. And in this case, I guess you would go Google it. So luckily, it appears in Python package index, and we can install it. So now we have successfully installed that module that was missing, but it still doesn't tell us really anything about the model and how it was structured. But it turns out we can unpickle it, and it has a nice representation in Jupyter notebooks that shows it's a pipeline. It's a Scikit-Learn pipeline, and we can actually query it as we can with all Scikit-Learn classes and get the parameters here, and we start to be able to see, oops, where do I press for pointer? Well, we can see at the parameters that there's actually also some information about the fingerprint part here. And as we can guess from the first transformer smiles to more, maybe we can actually just feed it smiles and it will return a prediction. So cool, how did we end up at this result? We did this at the hackathon. We combined two famous open source products, Scikit-Learn and RDKit. And we're using the transformer, we subclass the transformer mixin and base estimator from Scikit-Learn, which give us all that functionality that normal Scikit-Learn classes and transformer have. And then we suddenly have transformer objects that can take in more objects and return fingerprints or descriptors. Or we also have transformers that can turn smiles into molecules. And this turned into a project called Scikit-Mol. So if we are going to see how we can quickly build a model, it's about importing various Scikit-Learn classes and also Scikit-Mol classes. And then you can string it together in a pipeline. And you can then fit on a list of smiles and a list of your values you want to be able to predict, as we usually do. And then we can see, we can test the train score and the test score, and we can directly see how we can work with this in a direct fashion, where the featurization of the molecules is directly included into the Scikit-Learn model. So if we look at the various features, I think one of the main task it has is actually to turn molecules into features that we can use in machine learning model. And you can also just make a pipeline that does that, and then you get the features back and you can do what you want to do with it. But it can also be used to integrate it into Scikit-Learn classes. And that's nice because suddenly we get these kind of self-contained and self-documented objects that we can pickle, and we can later unpickle them, and we can go in and have a look at what are the features, how is it constructed, what are the hyperparameters of the entire stack from smiles or molecular object to prediction. So it's self-documenting and self-contained. And as it is Scikit-Learn classes and fulfill all necessities there, you can also build more complex structures and pipelines with Scikit-Learn. I show here an example of a pipeline that uses a feature union so that we both use Morgan fingerprints and also add some molecular descriptors. And we do some feature expansion with the polynomial features Scikit-Learn class, and then some feature selection with a random forest regressor before we have the final model. So we can actually also build more complex model. If that model makes sense, I mean, it's just an example of how we can use Scikit-Learn classes together. So there are a descriptor transformer, and we also have implemented various fingerprints, and there's also a conversion smiles to molecules, and some simple standardization to standardize molecules. And there are more examples in the notebooks on the GitHub repository. And there's also a little software note on the way where you can read more. So acknowledgement, we had a lot of excellent coders at the last RDKit hackathon that contributed either transformers or structure or Python package index integration and unit test and other things. And we also have had help of a graphic designer to design a logo there. And then, of course, this wouldn't have not been possible without the RDKit community and the open source project and the UGM organizers. So thank you very much.